welcome everybody. So far we've done up to talking about pH, POH, H plus and OH minus, and dissociation constant for water, Kw. We've also mentioned things like Ka for acids and how it affects acid strength. But now I want to talk to you about solving acid and base problems where you have a weak acid and they ask you for things like the pH. Something that's important before we get into that, when you deal with acid and base strength, sometimes questions appear where they're asking you about, what's the stronger acid or base, and they're not really giving you any information except about that there's a reaction that's occurring. And so the idea is that when you're given a reaction and you're not given the Kas or the Kbs of the acids or bases, you can always tell by what the K value of a specific reaction is. And the reason why is because reactions, they'll always proceed in a direction that will produce the weaker acid from the stronger acid, or the weaker base, from the stronger base. And so let me just show you this example down here without any further ado. So here I have my reaction where I have my acid, and it's reacting with the base, and then it's forming these products here. And they're saying that the Kc is greater than 1. And that means that we'll proceed to the right. So that means that these will be made. We're going to proceed this way. Since the weaker acid and base are favored, that tells us right away that this is a weaker acid and this is a weaker base. Let's try the next one. Here we have Kc less than 1. Well, we can identify that the reaction is going to proceed to the left, and so these are going to be our weaker. Now we just got to figure out which one's the acid and which one's the base. Well, H2O is donating, it's going to be the acid, and HS is accepting, it's going to be the base. And that kind of makes sense that those are weaker. Like H2O is a weaker acid than H2S, hydrosulfuric acid. And HS minus, hydrogen sulfide, is weaker than hydroxide. And so we kind of get that idea from this. All right, let's get into the real meat of this video, and that is the equilibrium problems. And so here's a problem where I ask you to find the Ka. And so I give you this acid, phenylacetic acid, and I tell you that it has a pH of 2.6. And it has a concentration of 0.12 molar. So I'll give you some fun facts about its biological functions. Well, let's go into this and see what happens. Well, I set up an ice table. I write out a reaction. It's the acid plus water, H3O plus, yields PAC minus. And then I write out an ice table. I leave out the water. Notice that is left out. I have my reactants and then my products over here. I can write a Ka for this. Same as any Kc I've always written. Doesn't include the liquids. And then I plug in my values. And so I have my initial values over here. My initial value for the acid is 0.12 molar. H3O plus, there is a little bit around. That's from the water dissociating on its own. But notice I just leave that and make it 0. And we'll do that from now on. And the conjugate base is 0 as well. And my changes, I use up my reactants, so minus X, and I produce my products, plus X and plus X. And then I have my, my equilibrium, where I have my initial plus my change. I have my initial plus my change, which is X, and I have my initial plus my change. Now the thing is that I know X because they tell me what the pH is. And so if I do 10 raised to the negative pH 2.60, I'm going to get the concentration of H3O plus, so I know what X is, and I know what this X is too. It's the same. And I can subtract that from 0.12, and I'll get this value. And then I can simply just plug it into Ka, and I can solve for the Ka value, 5.4 times 10 negative fifth. Just like all those other K values for acids and bases, they're small, and that's what we see here. So look, here's a practice problem for you. Conjugate acid is of NH3 is NH4 plus, a weak acid. I give you the concentration of that weak acid, NH4 plus, tell you the pH, ask you to find the Ka. So go ahead, give it a try. Remember the steps here. We're going to 1, set up an ice table. 2, write out a reaction. 3, we're going to plug in our values. We're going to find the H plus from the pH. And then we're going to plug those values in to the Ka expression. I would say by far the thing that people find the most difficult is writing out the reaction. That to them I think is where they get bogged down. All right, so try that out. We're going to go over it in class, see how you do. If you have questions, you can always ask me. All right, here's another one. Now I'm given equilibrium concentration. I'm asked to find, I'm given the Ka. I'm going to be asked to find the equilibrium concentrations. So notice the similarities here. Got my acid. I'm going to write out a reaction. So I abbreviated this whole part here, PR, for propanoic. So I have HPr plus water yields PR minus plus H3O plus. I plug those in. Notice I leave out the water. I don't even put the water in when I'm doing problems normally, but here I just show that you're going to ignore it. It's a liquid. So I have my initial 0.1, 0, and 0 are the products. 0.1, 0, and 0 are the products. Minus x for change, plus x, 0.1 minus x, x and x. Now on the side here I have the work. So I take the Ka, I make it equal to my expression, which is the products over the reactants. I plug in my values, and now I simplify. And remember in equilibrium, we did those problems where we had the 5% rule and we simplified. The x is so tiny, and we could check with 5% rule later on, but we don't have to. Because generally, when the K is this small, you're going to neglect that x down here, and we're going to just have this simplified setup. So I can solve for x. I get x is 1.14 times 10 negative third. And then I can solve for the pH. The pH is 2.94. I could do the same problem. Here's one with cyanic acid. And with cyanic acid, I have, this Ka that's 3.5 times 10 negative fourth. I'm given the initial concentration. I'm asked to find the pH, H3O plus. So go ahead, try that one out. Model it after the one that I gave you. It's pretty much identical. Okay, one last thing I want to talk to you about here is on this next slide, what happens if I change concentration. And I show you an example here. I just use a general acid. I use HA, any generic acid. I show you two different concentrations. I show you 0.1 and I show you 0.01. And I, tell you that the 0.1, that it dissociates to a certain extent. And I tell you that it makes this much. And this is going to be based on the Ka. We could solve this problem using the Ka. But when I have 0.01 molar HA, the amount of H plus goes down, and that makes sense. You have less acid, you have less H plus. Now the thing is this. They're both over the initial concentrations here. They're going to be times by 100. Look at what happens. Yes, in the more concentrated acid, you make more H plus, but it's only 1% associated. In the less concentrated acid, you make less H plus. That makes sense. But you're actually more dissociated. That's weird, but it's what happens. You don't actually get more H plus, but your percentage of dissociation is greater. And this is the question that they like to ask. It's like one of those one-off type questions. Okay, the last thing I want to show you is with polyprotic acids here. With polyprotic acids, we have an acid. This one has 3 H's, H3O plus. It dissociates, 1 H comes off. This product then dissociates again, and another H comes off. This dissociates again, and then another H comes off. And we get 3 different K values, K1A, Ka2, Ka3. If I asked you to find the pH of this acid, you wouldn't have to do this each time. You don't have to find the H3O plus that each one makes. You only use the first K. pH is of the Ka, number 1, look at how much bigger it is. It's about 100,000 times bigger, negative third compared to negative 8. That means that most of the H plus is coming from that first acid. And so we can just use that first acid and determine the pH. We can ignore the other Kas. And that's important to remember that you can do that. All right, so one last little thing, I know I said I would stop, but one last little thing is talking about Kb, which is for bases. And it's the same as Ka. I do the same things I was doing. I write an equation. Notice the base produces OH minus. I write a Kb expression. Same as Ka, except now it's for the base. And I can solve for my OH minus. I can set up an ice table, have my Kb. If I have my initial concentration, I can find my OH minus. The only difference with these Kb's is that when you find the OH minus and then you do the negative log of that, you're finding the POH. And then from there, you have to do 14 minus the POH. That'll get you the pH. So again, I'd love it if you could try this next problem here. So for this video, there's really 3 problems that you're trying. You're trying the 2 Ka problems, and you're trying this Kb problem. All right, so thank you so much for watching, and we're going to go over these problems in class, see what you get, and hopefully they're good. All right, thank you.